One second.
Good afternoon, everyone. The Office of PSA, FICCI and the Pune Knowledge Cluster welcomes you to the 13th session of the Innovation and Science at Bharat series. The session also marks the first of our sessions on quantum technologies. Building upon quantum capabilities is one of the most remunerative areas of technological development. From everyday functioning of companies to national security, quantum computing has a wide spectrum of applicability. The Quantum Frontier mission of the PMSTAC aims to initiate work in the understanding and control of quantum mechanical systems with a large number of degrees of freedom as one of the great contemporary challenges in fundamental science and technology. Building excellence in the quantum frontier through this mission is essential for national security and the development of quantum computers, quantum chemistry, communications, new materials, quantum sensors, and quantum cryptography. The next leg of the series delves into the industry-academia partnerships that are facilitating the mission. It gives me immense pleasure to introduce you all to Professor Umakant Ripal, Associate Professor at IISER Pune, who will be delivering today's lecture. He will be talking about what lies ahead for us in the quantum technology space. Before he can start, I'll introduce him briefly for our attendees today. Professor Ripal is an experimentalist in atomic physics and quantum optics. His research interests include using ultra-cold atoms and ions for fundamental research and quantum technologies. His current focus is on using current quantum matter for quantum sensing, simulations, and for precision metrology. Professor Rapal did a PhD at ISC Bangalore in 2003 and was a visiting researcher overseas after that. After spending about 4 years in industrial R&D research Bangalore, he joined ISER Pune in 2009, where he now leads the iHub Quantum Technology Foundation, a Section 8 company established at ISER Pune under the National Mission for Interdisciplinary Cyber-Physical Systems of Department of Science and Technology, Government of India. I now invite Professor Rapal to deliver today's lecture. Over to you, Professor.
Thank you very much, Sivli, for introducing me. Good afternoon, everybody. So let me share my slides. And before that, I would like to mention that it's my privilege to be invited for this seminar. And I'll try to do my best in terms of giving an overview of what lies ahead and what the current situation status is with quantum technologies in India and overall, but in India specifically, what kind of programs are being taken off and what we are up to right now. Okay, so yeah. So this is a picture of one of the setups in our lab and what most of the laboratories working with atoms and photonics and optics looks like in general when you go to any of these labs. But this is just a representative picture taken in my lab here. Okay, so what's quantum technology? That's a big question what everybody would be worrying about because there is a lot of focus that is being attention focus everything on quantum technologies all over the world, and there is a lot of funding that has been pumped into this in the across the globe in different countries through various national level programs and individual researchers also working in this quantum technologies. So, I mean, we know that last century, in the beginning of the last century, quantum mechanics was born, and we all know that, I mean, quantum mechanics was the only thing that could explain many observations that we see in nature at an atomistic scale and molecular level, all the phenomena that is going on, including the light emission from the tube lights and LEDs, all the physics that goes on was explained through quantum mechanics. Now, what quantum mechanics at that point, the striking features of quantum mechanics was that these existence of superpositions, entanglement, and the duality nature of particles and waves, all these basically got into the theory through a proper evolution of these concepts, it got into physics, into explaining various of these phenomena. Now, after a century or so, and over the last century, I mean, we have used quantum mechanics extensively to explain all the properties of solids, how electrons are transported within solid, and starting from there to many, many other areas of physics. Now, we have entered this era of quantum technology. How is it different from what we know about? I mean, we term this new era as second quantum revolution, where what the world is doing is that trying to use these delicate and intriguing features of superpositions of quantum mechanical states, entanglement of particles or different physically separate systems, to exploit these features to build various technologically applicable devices. Now, the biggest buzz around this is to build quantum computers, which are projected to be much, much faster than what our classical computers can do at the moment. I mean, even the fastest supercomputer is going to fail and is not going to be able to solve certain problems which only it is thought that using the principles of the superpositions and the states of the quantum mechanical systems can be used to build computers to churn out numbers or to solve certain problems in a much, much faster way. Second, to build networks for information transfer into a very, very secure network wherein one cannot actually, it is impossible to do any eavesdropping on information that is transferred from one position to the other. So that is secure communications, which relies upon, again, the principles of superpositions, the principles of entanglement, and principles of impossibility of cloning a quantum mechanical state. Then, of course, we have the prospects of building better sensors for various applications I will show you. And all these rely upon utilizing these principles of superpositions of these quantum mechanical states. Then, of course, I mean, when you go to the single individual atomic level, one can build clocks that can lose a second over a billion years or so. So this is the current record is that 1 second, you hardly lose a second in 10 to the power 19 seconds or so, which is way, way, way longer than the known age of universe. So one can build better atomic clocks using this. And using both this, building better sensors for different applications, including navigation and rotation sensing and gravitational acceleration sensing, together with these atomic clocks, one can build superior navigation devices, which, for example, can be used in deep space navigation where you don't have any signals. Now, I have just listed out a few applications of what quantum technology can be used for. So, as I said, I mean, quantum computers, quantum sensors, and these atomic clocks can be used for, say, doing faster drug design and faster drug screening. See, for example, if you take a large molecule, it is difficult, it is practically impossible to actually calculate all the molecular structure and how the molecule behave based upon the structure. The behavior of the molecule is most of the times decided. And that at the moment with existing computers, it is a very slow affair to do large calculations for very large molecules. Now, once you have these quantum computers fall under two categories. Completely programmable quantum computers where you can actually build the entire logic, and the other one is analog quantum simulations where you build a system which mimics a particular geometry of a molecule and then do a simulation which gives you an output which is an analogous output to the exact actual problem. Now, this can be used for designing better materials, for example. And when you talk about quantum sensing, there are vast applications. Like, for example, if you can measure magnetic fields very, very precisely, and with these atomic magnetometers or magnetometers based upon nitrogen vacancy in diamonds, for example, can be used for sensing uh, magnetic fields around the brain, and one can also do low field imaging, anatomical imaging, which is of vast importance in healthcare, for example. And the quantum communications that I talked about, those can be used not only for this secure communication, but also once you have a secure communication, then it is extremely important for fintech, for cyber security, and many more applications one can think of for strategic applications. The other thing is one can use this extremely precise gravitational acceleration sensors, which are built by uh, using the wave matter duality. You build interferometers with particles instead of light, and then those can be used for very accurate sensing of local gravitational field up to eighth or ninth decimal. We all know only up to, we study in school only up to 9.8, I mean, first or second decimal, and that number we know very well as 9.8 meters per second square. But you can actually measure, go up to eighth or ninth decimal, and once you go up to that eighth or ninth decimal, then you can start seeing differences in the composition of underground materials in the earth, different kinds of things, and you can actually probe things like map things like tunnels and whatnot within underground. For example, here is a picture of a pyramid with a lot of tunnels and passages. If you take one of these gravimeters and move them around, you can actually, in principle, map out the different hollows which are there, cavities inside this structure. And as I said, these atomic clocks, which hardly lose a second in 10 to the power 19 seconds, can be used for deep space navigation, including these precise rotation sensors. One can use them for navigation of satellites which are sent into deep space, which do not have any radio, sometimes do not have any GPS connectivity, obviously, because there are no other satellites which are giving them signals to locate them. They need to have their own autonomous navigation systems, and there these sensors are useful. And this is what I mean by atomic inertial sensors. Once you mount them in some space flight, then you can actually sense all these X, Y, and Z direction rotations, which can be used for navigation. Now, so what all does this quantum technologies have? So broadly across the globe, it's the different uh, technologies, sub-technologies within the quantum technology umbrella. They have been divided into four broad verticals. The first one is quantum computing. Of course, that is one area where a lot of resources are being pumped into to build better and better and faster computers. Now, here are some examples of such systems. Now, quantum computing is actually based upon two-level quantum mechanical systems like atoms, photons, ions, or superconducting circuits. I mean, currents flowing in Josephson junctions, which can be used as two-level systems, which can, in principle, exist in the well-defined ground and excited states, plus they can exist in superposition states. Now, so some of the requirements that exist for using any of these quantum mechanical systems, they are called as, there is a criteria which has to be satisfied for them to qualify for being utilized for a quantum computer, and those are called dimensions criterias. And the idea is you should be able to initialize these bits, qubits. Like in classical qubits, you should be able to set them to 0 or 1s. You should be able to read them out. You should be able to uh, make two qubits talk to each other through some interaction, so that you can execute what are called as two qubit gates. And there are many so I've taken some of the I've just told some of the important criteria these qubits have to satisfy, and some systems like ions, atoms, and superconducting circuits, as I told, they actually satisfy all these criteria. So here is on the this is a company named IonQ, which has built an ion trap commercial, which is building a commercial ion trap quantum computers where the number of qubits can go beyond 50 or so. And this is an example of another three-dimensional ion trap architecture where ions are trapped inside these four electrodes which are there in the center here, and then you can actually image the ion. So each of these dots here is a fluorescence from a single ion, and you can actually control the state, internal state of these ions, and actually use them as a quantum register. Honeywell has also started building, has been successful in building a practical ion trap quantum computer, and then IBM is also the biggest competitor in the market, who is come up with more than 100 superconducting qubits quantum computer. Now here on the bottom side, which I'm showing here, is these yellow dots here is an array of fluorescence from an array of atoms. Now this is an array of uh, rubidium atoms, which are trapped inside in periodic array of potentials. And actually one can create 2-qubit gates or 3-qubit gates, or actually create a network of these atoms which can be interacting, as it's shown here, through what are called as Rydberg excitations. So you can create a, so these atoms are spaced by about few micrometers away, and by doing what is called as a Rydberg excitation, which is shown in this blue halo here, by taking the electron to a very highly excited state, one can actually generate a very large electric dipole moment. Now, when both neighboring atoms are excited to this high electronic excited levels, then they start repulsing each other, in the sense they start seeing some repulsive interaction, and that this interaction can be used for either generating an entanglement of neighboring atoms, or can be used to make neighboring atoms interact. And these systems have been used to simulate certain quantum mechanical Hamiltonians, which can actually be generalized. The Hamiltonians can be engineered to suit a particular problem. For example, initially I was talking about this simulation of molecular structures. For example, one can actually create, say, in this two-dimensional array, one can also create a three-dimensional array of these atoms, and actually make these atoms interact only in a certain manner. Only certain neighboring atoms or certain atoms can be made to interact, and make them look like a particular molecule, and do the quantum simulations. So these are some examples of quantum computers, analog versus digital and digital. Now, quantum communications, as I said, what are these quantum communication? See, there is a fundamental principle of quantum mechanics wherein, once you have a quantum mechanical state defined by defined by a wave function, or ket some state, then you actually cannot copy that state onto another quantum mechanical state. This is called as a no cloning theorem. Once you try to do anything to a quantum mechanical system which is in a particular state, if you take a superposition of 0 and 1, it immediately collapses to either 0 or 1. So you cannot copy the state. So this is what is used in quantum communication. So you send information via two channels. One is a classical channel, which could be your fiber optics based digital transmission, or through radio frequency communication, you send a classical information. Parallelly, you send these photons, where you encode the information that you want to, the secure information that you want to transfer. And then by comparing, you can actually know whether the information has been eavesdropped on the way or not, and you can ensure that the information is transmitted from point A to point B in a very secure manner. Now, here in the picture here, this is a picture of a demonstration of satellite-based quantum communication between two ground states. So the challenge in these long-distance quantum communications is sending photons from point A to point B, where the distance between point A and point B decides how many photons you would lose on the way. Because once you send photons through, for example, atmosphere, then there are a lot of things that the photons are going to interact with in the atmosphere. Atmosphere has all kinds of molecules, which the air is composed of all kinds of molecules, which can scatter photons, can absorb photons and rescatter them. and there can be dispersion also, which will spoil the state of the photon. So all these are actually will interfere with the photon. The challenge is to choose the right wavelength and the right amount of the rate of photons that are emitted from point A to point B, so that the loss is minimal. So, and people have demonstrated this kind of a communication over thousands of kilometers. And the other thing is, since we know that photons are going to be lost on the way, there are new concepts that are coming up, and that is called as uh, m- building what are called as quantum repeaters. So in classical repeaters, when we send a signal over an optical fiber, once the signal gets attenuated, which means the light gets attenuated, you just put it in a photodiode, amplify that, detect that signal, amplify it, and feed it into another laser diode and send your digital pulses, which is our classical information. Now in quantum mechanics, you cannot do that direct copying because of the no cloning theorem. But what you have to do is you have to um, do what is called as teleportation. So you do either an entanglement swapping or a teleportation and copy the state, not literally copy, but map the state onto another photon and then send it. So quantum networking is something that is also a part of this quantum communications. Third vertical is quantum sensing and metrology, which I mentioned. Now here, as I already told you, there are various types. There are spin qubit based sensors wherein you have an electronic spin inside a solid matrix of some condensed matter system, and then that can be used for the spins can be electronic spins can be used as sensors. Then you have these atomic sensors for inertial navigation. This is based upon atom interferometry. Like we have in optics, a Mach-Zehnder interferometer with light, you build an interferometer with photons, and those will, and with atoms, sorry, and that several orders of magnitude better precision and accuracy than sensitivity than what photons can give. Then, of course, this quantum clocks, which I told you about, these are basically you trap single atoms in certain traps which are made out of light, and then you interrogate very narrow optical transitions, which have a very high quality factor. These resonators act as very, very high quality factor resonators, which can be used, which are being uh, exploited for building very high accuracy timekeeping devices or clocks. Now, light. I mean, squeezing of light is another part of this. So once you take a laser light, there is going to be noise in amplitude and phase, and there is a minimum amount of noise that you can that you can get because of the uncertainty principle in quantum mechanics between the amplitude and the phase of the light. Now, there are ways to actually decrease the noise in one of those variables, either the amplitude or phase, and can generate what is called as a squeezed light. And one of the best applications what squeezed light has seen is in actually increasing the sensitivity of the gravitational wave, LIGO gravitational wave detector. The other thing is using these entangled photons, one can actually do imaging of hidden objects. So this is some piece of some template of a cat which is put inside the medium, and by putting entangled photons through this system which is invisible and then doing some interferometric measurement of the entanglement, one can actually deduce what is there inside, hidden inside the turbid medium. So that is one application where you can use entangled photons for detecting hidden objects. And of course, one can use these quantum mechanical systems for building standards for, say, voltage and magnetic fields, which are some of the primary standards in the measurements, the physics of measurement of physical quantities. There it can be used. The fourth vertical is on quantum materials. So what quantum materials is basically is that all solid state systems, either three-dimensional or two-dimensional solid state systems, where you start playing with the electronic spin or electronic charge within the device for building devices that can store information, building devices that can sense magnetic fields, building devices that can sense photons, for optoelectronic purposes, and even maybe design materials which can uh, get us a better understanding of, say, for example, superconductivity. So quantum materials is a broad area. It is basically the entire condensed matter systems, but with material science and condensed matter physics with a slight twist, wherein you start playing with the physics at the atomistic scale in 2 dimensions or in 1 dimensions. And here are some pictures of such materials. For example, here is some representative materials, for example, black phosphor, graphene, um, molybdenum disulfide, etc. These are 2 dimensional materials which can be used to detect with very high sensitivity the visible light, and which is of very high importance in single photon detection and many other applications, wherein for example, the single photon detection is with very high quantum efficiency is important for quantum communications, for example. And of course, here are some structures which can be designed, for example, to capture light very effectively in such a manner that you can increase the sensitivity, increase the efficiency of conversion to electricity from sunlight. So to increase the efficiency of solar energy devices. There one can engineer these materials and use the principles of these superpositions and entanglement to actually capture more and more photons and convert them into something very useful. Okay, so that's about what different quantum verticals of quantum technologies are. Now, going forward, now in India, there have been a lot of initiatives that have taken off in the recent past. For example, there is a quantum enabled science and technology program of the Department of Science and Technology that got kicked off last year, in the beginning of last year, and where there are about 50 projects under this program funded by over 200 crores. And these 50 projects are spread over those 4 verticals. And already we are into second year, and there has been a lot of progress that has been made in many of those 4 verticals. Now, and recently at ISER Pune, the Department of Science and Technology has established a quantum technology innovation hub called as iHub Quantum Technology Foundation, which is a Section 8 company. The idea of this is so this is part of the 25 hubs that have been established under the National Mission for Interdisciplinary Cyber Physical Systems. And of course, there is another center of excellence that has been established by funding from Ministry of Information, Electronics and Information Technology at Bangalore, between the 3 institute, IISc, Raman Research Institute, and CDAC. So this is a center of excellence that has been established where there are a couple of programs that are going on. And apart from these programs which are going on in academia, there are many programs that have started in government agencies, different government agencies like DRDO, ISRO, Department of Telecom, and CDAC, various programs that have started independently. And of course, we are looking forward to this big national mission that is coming up on quantum technologies. And there, these activities will be taken off in a much high, with much greater energy. Now at I have Quantum Technology Foundation. So this is what I'm showing you, what we are doing here to take forward these quantum technologies. So the main thrust of this center is going to be in technology development, development of human resources, and develop very high skill set in the area of quantum technologies, and at the same time do basic research wherein you work on uh, project going to feed into real applications in the future. And the three were technology verticals where we have classified ourselves here is quantum information and metrology, quantum communications, and quantum materials. Now, the grand problems that we are going to be addressing soon are listed here. So the first one is build a fully programmable more than 20 qubit quantum computer and build quantum simulators with 50 or more qubits for doing analog quantum simulations, and put at least a 20 qubit quantum computer on the cloud for usage in India by all the other academic and other companies, for example. Development of, so since the focus of this hub is in technology development, we are going to focus on certain things which are also kind of well established in the industry abroad, but we are also going to do a lot of indigenization effort, and that is this development of detectors, light sources, and of course the quantum repeaters are still at lower technology readiness levels. So those work we will pick up, and we at ICER Pune we are building a strontium atom optical clock, and at Tayuka Pune they are building an ytterbium ion based optical clock, which we will synchronize. The distance is about 5 kilometers, so this is for synchronization of optical atomic clocks. Then, of course, developing indigenous quantum sensors for photons, develop these inertial sensors, atomic clocks, etc. Then a lot of devices using these quantum materials. And parallelly across all the verticals, our focus is going to be on indigenization of very key technology enablers like materials, devices, instrumentation, control systems, algorithms, and software for quantum technologies. The roadmap is basically this. So we have design stage, construction of hardware, laboratory demonstration, prototype development, and technology transfer spread over 5 years. And the color here shows the technology readiness levels. The scale here is the technology readiness levels. Now, on the quantum computing side, we will be working on quantum computing with trapped ions and also trapped atoms in our lab here, superconducting qubits based quantum computers, NMR, nuclear magnetic resonance based quantum computers for demonstrating this more than 50 qubits NMR quantum registers. Then this nitrogen vacancy centers based quantum computing. And these nitrogen vacancy centers are also going to be used for metrology applications, for sensing applications. And the idea is at the end of the day, doing a technology transfer at various stages, wherever there is some development and there is scope for commercialization of these enabling technologies and systems, there will be work on technology transfer. On the communication side, the main focus is going to be on these quantum repeaters based upon hybrid atomic and photonic systems, which is based upon trapped atoms and trapped ions together with optical cavities to actually map the entanglement onto the photons and sending them over large physical distances for the secure communication and for building quantum repeaters. In the quantum metrology and the plan is on building this strontium atomic clock and also ytterbium atomic clock, and then building a fiber link between the two clocks for doing a phase stabilization over, locking the two frequencies over long distances, which will be useful in the future. NV centers based quantum metrology. So these are nitrogen vacancy centers in diamonds, which will be used for mapping magnetic fields, etc., very precisely. Then in quantum materials and devices, as I said, there are many horizontal spintronic devices, optoelectronic devices, multifunctional quantum materials, and looking at the materials which have emergent phenomena. And of course, as you see in the bottom, all of these verticals have this instrumentation and technology support systems, which is a common denominator for all these technologies. So there is going to be a huge focus on translating the know-how into products and spinning off companies. Now here, I'll quickly give you a glance of the projects that are going on at ICER Pune related to quantum technology. So we have started building this strontium atomic clock, where here, this is a setup where we are still building it. And inside this, we have a cloud of, this is a bright fluorescence from about 1 billion atoms of strontium atoms. And these atoms will be transferred into what are called as one-dimensional optical lattice, and we will use them for the clock application. Then we have developed a laboratory prototype of a gravitational acceleration sensor, which is called as a gravimeter, which at the moment has reached about 1 ppm sensitivity, and we would like to push it by a few more orders of magnitude. And parallelly, we are developing a portable device, concentrating on making the device more compact so that it can be transported for geological mapping as well as for hydrological applications. Now, this is an NMR center where my colleague Mahesh is working on developing these 50 qubit NMR quantum register, and he has recently worked on simulating the charging and discharging in a battery using spin qubits. And this is one application of simulating using this for energy applications. Now, other project my colleague is working on is he's built a setup where you can actually probe single individual nitrogen vacancy centers in diamond. And this is a map of different nitrogen vacancy centers fluorescing inside the diamond, which are naturally embedded. And this will be used for building the quantum qubits register for quantum computing applications in a solid state system. There is some work going on with quantum materials also. My colleague Dr. Sunil Nair is building these spintronic devices where electronic spin current is induced by applying electric fields, applying a current, which can be used for storage of information and as well as sensing application. Now, how do we, succeed in this quantum technologies area in particular? So it involves collaboration between different domains. One is large industry, academia, startups, and end users. So all of these people have to come together, and then different. So the academia in India, there is a large pool of academicians, experimentalists as well as theoreticians who have a good knowledge about the quantum technologies. And as I mentioned, these 50 projects that are being run under the quantum enabled science and technology program. Those 50 PIs spread over many IITs and universities and some national labs. Those people, together with industry, have to come together, and whatever technology is developed within academia, that has to be translated into products by nurturing startups through the students who are got trained, through the students and senior scientists who get trained in this academia. One needs to incubate these startups. So one of the aims of our hub is to do that. So all the academic partners that we have together with ISER Pune, we are going to incubate startups within this uh, innovation hub, and then also collaborate with large industries so that some of these products which are developed can actually be translated into for mass production. Some of the things can actually be for mass production, and these products can finally feed into various applications for communications, for healthcare, for biological sciences, for security, and for space applications. Now, there are various technology enablers that one needs to become stronger in. And the knowledge exists in bits and pieces, and it's kind of scattered all over the country. And uh, these technologies and knowledge have to be pulled in together by bringing in agencies which have that know-how. For example, these are some of the list of things that one needs to be very strong in, and I think we as a country overall have expertise in many of these. Especially we are leaders in software development and electronic device design system, electronic systems design. I think there are quite a few agencies within the space agencies and defense agencies and other private agencies where they do a lot of electronics device and system development, including RF electronics, We need to become stronger in optical systems designs as well as manufacturing of optical components, which is very crucial to become completely self-sufficient, including simple things like mirrors and beam splitters and polarization optics and things like that. Those there we have to become stronger to become self-sufficient. And then, of course, while we are consolidating all these different technology areas, we need to increase the emphasis on giving specialized quantum technology courses across the country. So here we are thinking of starting an MTech quantum technology program. A similar program exists in IISc now. And through these courses, although the basics, the fundamentals that are needed for this quantum technology, those are taught at different levels at undergraduate and postgraduate level. But there is not a single program which actually brings all those together for targeted applications for quantum technology. So that is something which we are thinking of starting. So these are the things that need to be got together. And that's all I had to say. Thank you all.
Thank you, Professor Paul. Thank you for giving a very comprehensive view of the quantum technology research happening at IISer Pune and across the country. So there are a few questions. I'll start with the one on fellowship opportunities available at different levels for research in quantum technologies.
Yeah. So I can tell you about the two programs that I am well versed with. One is the Quantum Enabled Science and Technology program, which is already running. So there are a lot of PhD and postdoctoral level openings still available in this Quest program across different PIs. And other thing is through this Quantum Technology Innovation Hub, we have recently launched this Chanakya PhD and postdoctoral fellowships, which have been this first year we have already sanctioned some of these positions spread across the country. And we are evaluating the applications for undergraduate and postgraduate project students. Those are Chanakya UG and PG fellowships, which are going to be there over the next 5 years. We will be coming up with these advertisements frequently. The first year, before March, we have already finished these advertisements and releasing of funds for this.
Thank you so much. The other question that I had was, what are the industry problems that different research institutions are working on in this space?
Industry problems directly at the moment, as I said, if you look at those four verticals, computing, communications, sensing, and the quantum materials part, I don't think there is a direct interaction yet between Indian industry and this in academia. But I am aware of one or two companies which are in the quantum communication space, in quantum key distribution, etc. And of course, the space agency is working together with Raman Research Institute for some of the quantum communications related work. And for the quantum sensing part is something where we already have the technology at some maturity level, which in the lab, which needs to be translated. So from our side, at least from our hub and from ICER side, and with our collaborators together, we will be soon starting these interactions with industry and also maybe even start a startup at the hub and other places maybe for translating these sensing activities into products.
Sorry.
Yeah.
But thank you. That would be all, Professor Rapal. Thank you very much for joining. The Office of PSA has been bringing together industry partner startups and academic institutions to develop innovative solutions to support different R&D sectors through
Yeah.
this initiative. And you want
Yeah,
me
in
to add
that
something?
matter, yeah, just wanted to add something on that.
Please.
Maybe at some point, we should think of since slowly things are opening up now from the pandemic. At some point, maybe in a couple of months, we should probably, I mean, your office should probably think of joint industry academia symposium in quantum technologies.
Sure.
I think
So,
that,
Professor Paul, I'll have that conversation with you
yeah, sure.
after we end this event.
Yeah, yeah,
Thank
yeah,
you very
yeah,
much for
sure.
bringing that up.
Yeah, thank you very much. Yeah, thank you, thank
I'm
you.
really grateful
you.
to my team, to the teams from Pune Knowledge Cluster and Fiki for helping us out in putting together this series. If you missed this session, you'll find the video on our YouTube channel, and you can download the presentation that Professor Paul gave right now from our website. Thank you very much for attending today's session. See you again in March. Thank you.
Yeah, thank you. Bye.
Bye.